Hello, in this video I'm going to give a quick introduction to our next big topic, which is the structure of matter. And I think this follows on nicely from what we've been doing so far, which has all been classical mechanics. Because in classical mechanics we've been looking at macroscopic objects. So these are objects with mass and volume that we've been considering, but we haven't been interested in their internal structure. We haven't been looking at anything inside these objects. They've just been these blobs. And then in classical mechanics, we've been seeing how they move around and how forces affect the motion. Now, in this new topic, the structure of matter, we're going to start looking at the internal structure. So we're moving from the macroscopic to the microscopic. And that switch from macroscopic to microscopic is also going to bring a switch from classical physics, which is what we've been dealing with up until now. So this is your sort of pre-20th century physics, the stuff that's still pretty accurate, but not as accurate as our most up-to-date descriptions of the universe. And we're going to move from that classical physics into modern physics. So this is going to be a lot of stuff that was discovered and descriptions that were created during the 20th century and even the 21st century. So we're really coming up to date with this. So we've got those two big switches from macroscopic to microscopic and from classical to modern. Okay, so here are our four main topics that we're going to be looking at inside this section on the structure of matter. We're going to start with particle physics. This is where we're looking at the fundamental particles that constitute all matter. So by fundamental, I mean these are the smallest bits that you can break matter down into, and there's a surprisingly small number of these considering the variety of stuff that we see in the world. So we're going to be looking at these fundamental particles, how they interact with each other, what their properties are, and how this is all contained, at least at the moment, in what's known as the standard model of particle physics, which is, it's not without its problems, but is the best description that people are working with at the moment. So we're going to really have that focus on fundamental particles. Then within that particle physics section, we're going to look at how those fundamental particles aggregate together. So how the microscopic aggregates together to make the macroscopic. So this would be aggregating up to make things like atoms and then into molecules and then into bigger stuff. So that's what's going on in particle physics. It's about what are the fundamental building blocks of matter, how do they interact with each other, and how are we describing all of that, which also include things like Feynman diagrams, which you might have heard of, which is a pictorial way of describing the interactions between fundamental particles. Now, when we get up to the atomic level, you start getting this sort of grey area between physics and chemistry. So chemistry starts to get more interested in what's going on with the electrons and then how atoms will be interacting and bonding together based on the electrons, whereas physics starts looking more at the nucleus of the atom. So our next section will then be nuclear physics. So we're going to be thinking, well, how is the nucleus held together? How is the nucleus structured? What's going on inside the nucleus? When does it become unstable? Because when the nucleus becomes unstable, you start getting radioactivity. Atoms can start splitting apart or start spitting bits out of the nucleus of the atom. So we're really having a focus there on the nucleus of atoms and when they become unstable and the radioactivity that's associated with that. Alongside that, in nuclear physics, we're going to look at the uses of nuclear physics. So stuff to do with fission and fusion. So fission reactors, fusion reactors, which a lot of countries are trying to develop at the moment with varying success. So yeah, we'll start getting into that side of what nuclear physics can be used for. And then at the end, I'm going to touch on, again, just to clarify the distinction, this grey area between physics and chemistry, because it's useful to know where physics is ending and chemistry is starting. I mean, as I say, it's a bit of a fuzzy boundary because, somewhere we're going from the absolute fundamental particles here inside physics. This is what we're describing in physics, in particle physics. and then we're ending up at the macroscopic objects that we've been looking at in classical mechanics. And then you've got chemistry sort of sitting in between all of this, looking at atoms and molecules and things like that. So it's worth trying to get a clearer picture of where the dividing lines are between physics and chemistry, because there's an enormous amount of overlap. So that's going to be the basic path that I'm going to take through all of this. First, look at the fundamental particles in particle physics, then look at the nucleus of an atom in nuclear physics and radioactivity, and then some distinctions with what's going on in chemistry. But before we start all of this, the first video I'm going to do on the mass energy equivalence, which is Einstein's famous equation, E equals mc squared, which is a game changer from the assumptions that we've had previously in classical mechanics and what we were setting up right at the beginning of all of these videos in the series. So we've got a real change here to our assumptions. This is a change that's bringing in modern physics and taking us away from classical physics, and that is the equivalence between mass and energy. So that's where I'm going to kick off in the next video.